Hello again. We are continuing our conversation about section 4.3, differentiation of exponential and logarithmic functions. In this second video, we're going to focus on the latter half of that, the logarithmic functions portion of this. And we'll do an application with logs too. Let's get there. Okay, so what we had tackled in the last video was the derivative of e to the x in its various forms, whether it's being combined with something else by a product, so we had to use product rule, or maybe there's some kind of composition going on, so we have e to the more complicated stuff. So we had a chain rule for e to the x and so on. So it makes sense to talk about the counterpart there, natural log of x. And so what we get is kind of unexpected, so at least the first time I ever saw this. So if we pick a positive real number, it's important that it be positive because natural log of x isn't defined if x is 0 or negative. Then what we get is the rate of change in natural log of x is 1 over x. The answer has no natural logs or e's or anything. So this is kind of unexpected, and when I first saw this, I didn't have the integral calculus perspective on it, but this isn't that surprising by some definitions of natural log of x. But at any rate, if we take a look at positive values for natural log, we get this function which is positive and increases at a decent rate at first, but then tapers off pretty dramatically. So remember, this is an e to the x function that has been reflected over the 45-degree line. So e to the x grows really rapidly vertically, so this grows really rapidly, but only to the side. So it's not going up by a lot as we go farther to the right. But the claim is that if we pick a particular x value, then the rate of change in this function at that value is equal to 1 over that x value. So the slope here is equal to 1/3, which is interesting. I mean, it makes computations relatively nice. Okay, so a quick example to get us in there. We've got x's and natural logs. They're combined by a ratio like this. We've got x's on top and x's on bottom. So in order to tackle that, we're probably stuck with quotient rule. So if we do that, we get our low d high. So here's our low portion. Derivative of the numerator is 2x. And then we subtract the other combination. So x squared, there's the top. Derivative of the bottom. Well, okay, so technically this would be derivative of 1 is 0. And then we'd add on the derivative of natural log of x, which is 1 over x. But that's what leads us here. So we get just that fraction, 1 over x. And then, of course, we're supposed to square the bottom. With a little simplification, we get something that looks like that. And just to double check where that comes from, we get 2x minus 2x natural log of x. So the 2x ln x isn't going anywhere. But over here, actually, let me do one more color. We've got all of this stuff, x squared times 1 over x. This is really just x. So in fact, we have 2 x's from this first blue thing minus this other x thing from the cyan, and so we're down to just x by the time we're done, combination of 2x minus x. Okay, so there's our derivative, just gets us one little glimpse and familiarity with these computations. So just like for e to the x, we have a chain rule for natural log as well. So if we've got something interesting stuck inside this natural log, so instead of just natural log of x, it's natural log of some other function, then we get to do this chain rule thing. It's 1 over stuff, so the stuff inside of the natural log function, and then times the derivative of that inside. So this has that same feel of power rule when we had stuff in parentheses to the 60th power or something. And we get to just do power rule and tack on the derivative of the inside. We could actually do these by a similar process. We could use the change of base formula with natural log and just get these things. But it's worth at least mentioning if we had derivatives, if we had functions other than e to the x or natural log of x, we can still do this in general for things that look like constant to the x power or log base something other than e of x. So these are the derivatives in those cases. So you might, just to note the special cases here, if we had e to the x, then this result still holds. It would be natural log of e times e to the x. But natural log of e is just 1. So this doesn't actually disagree with the numbers we came up with before. If we do the same thing for log, natural log is log base e. So if we do log base e of x, then we're supposed to get, for the derivative, we're supposed to get 1 over x times natural log of the base? Well, natural log of e is, once again, 1. So this is consistent with the definition we had just a couple of slides ago. We get 1 over x when all is said and done. So these aren't contradicting things that we had come up with before. They're just giving us others more general cases for this. It doesn't just have to be e for the base. Okay, so we're going to try a word problem out here. So our job is to look at the total number of hits that this website receives. So this is h of t is 200 natural log of t plus 4. These are in months after the beginning of 96. And then we found weekly revenue. So this is how much money they get per hit. Maybe this is from advertising or something like that. So the weekly revenue is found to be 25 minus 0.1 t. So the question that we're supposed to answer is, how is total daily revenue changing at the beginning of 2005? So as usual, we want to step out of the section that we're working on and try to think, how would I recognize what's going on here without knowing which section this problem is from? So if we step out of the notion in the back of our head or consciously of knowing that we're in section 4.3 and instead think, what sort of phrasing tells me what to do? So total daily revenue is not a function that we have at the moment, but we can build it out of the pieces we've been given. This is revenue per hit. This is the total number of hits. So I could think of revenue in this case, here is my quantity, the number of hits that come in, and here is my dollar value per quantity. This is the price in some sense. So this is asking the rate of change in that function. So I need to build R, figure out what its derivative is, and then this at the beginning of 2005 deal gives me a timeline to work with. So at the beginning of 2005, then let's see, beginning of 96 is where t starts out. So we would want, let me get it back. We would want r prime, and then I can do this in years, but 2005 to 1996 is 9 years. That many months is 108 months, 12 times 9. So this is our goal. This is what we need for this problem. So deconstructing these words and turning them into something mathematical, what I really want is r prime of 108. Okay, so rate of change in revenue is the derivative of this product. So the revenue thing that we want to put together is the product of these two functions. So here's r, and number of hits times revenue per hit. So we're just going to replace those two functions in here. Here's the hit function. Here is the revenue per hit function. So the total result of this is going to be something in dollars. Then we're going to take the rate of change, well, or maybe the units are actually slightly more complicated than that, but it's going to be a unit of money, whether it's hundreds of dollars, thousands of dollars, etc. And then the derivative is going to make this something out of time. So some kind of dollars per month. Okay, but staring at this, I see that there are things with t's in it, natural log of t plus 4, and then another quantity with t in it. So I'm going to have to use product rule. And I'll do it such that we're taking the derivative of one of these expressions. I guess I'll take the derivative of the 200 piece first. Then we'll leave the other one alone, and then we're supposed to do the other combination. So if we take this guy, derivative of 25 minus 0.1 t. Okay, so now using product rule, we've broken this down into two smaller derivatives to take. So the first one is actually where the new stuff comes in. The 200 is going to sit there, but natural log of stuff has a derivative of 1 over stuff. So the stuff that was inside the natural log is t plus 4. And then because this was more complicated, chain rule tells me, oh, you can't just ignore this stuff. By the time you're done, you have to tack on the derivative of that stuff. So inside here was the t plus 4. That's a funky box. The derivative of that is just 1. Derivative of t is 1. Then we're supposed to just leave 25 minus 0.1 t alone. And then the next derivative is this piece. But this is just power rule. We've got negative 0.1, and that's our result down the bottom. Let me get green back. So There's no more derivatives in this expression, so we've done all the calculus that we were here to do. Okay, so there's our derivative function, just tidied up a little bit, putting some fractions together, getting rid of the times ones that don't really need to be there. So this is our derivative function, but if you remember in our setup, what we really wanted was to plug in a particular value. So since the beginning of 2005 is 9 years after the beginning of beginning of 1996, that's 108 months worth of time since t is in months. So our prime of 108, we dump 108 in for our t's up in our original equation up here, and then get a number like -69 and some change. And as I mentioned, the units, we need a second to kind of crank through, but we can do this. So the units on h are in thousands of hits. Units on r are cents per hit, so it's not actually in dollars. And then the unit on time is going to help us out with the denominator. So basically what we should sit with is, we know that it's going to be months on the bottom, so let's just leave that alone. The only piece that requires some work is thousands of hits times cents per hit. So the piece that's kind of weird about this is that we have thousands and cents. So we could just write in terms of cents. That would not be the craziest thing in the world, but a cent is 0.1 of a dollar, 0.01 of a dollar. So if we wanted to write this using dollars, then this is 1/100th times 1,000, which is actually $10. So the units on how many hits the website receives go away, because that's hits per hit, so those cancel out. So the only thing left to figure out is this 1,000 cents written in terms of dollars. So we make that happen, and then we write one of our classic derivative interpretation statements. At the beginning of 2005, the daily revenue was decreasing because we had -69 for our answer, and then this is multiplied by 10 because of this whole $10 per month situation. So decreasing by about $690.13 per month, or in other words, for each month that passed from that point forward. Okay, so there's the derivatives of natural log stuff and other logarithms. That's it for section 4.3. We'll be back with the last section in the chapter.